Hello everyone and welcome to Java Basics. We have a cool Wordle clone, but it's still not a complete app. We need to save the data somewhere. We need to know which user solved the word, how many steps they took, and so on. How do we do that? We use a database. In this video, I'll explain what they are, the big ideas you need to understand about them, and we'll even use a simple database to get started. The code for this video is available here. It's in the description too, so don't forget to star and follow me on GitHub while you're there. And here too while you're at it. We used files when we needed to save things as we were building the initial command line version. What's wrong with that? Files are great. Let's say we have a web application and a user made a Wordle guess. We write that guess to the file. Then another makes a guess while we're still writing to the file, and another makes a guess while we're still writing. We're happy that our Wordle is popular. But if we're trying to write three different things to the file, it will become corrupted or some requests will fail. Files are great, but they weren't built for those scenarios. Databases are organized so we don't step on each other's toes. You can do multiple things at once and the database will handle that correctly. It does that with several tools, including based on the arrangement of data. I'll focus on relational DBs because it's the most common type of database and they're actually pretty great. In a relational database, data is stored in tables containing cells and rows. Typically, a row would have a primary key that represents it. In the case of the products table here, it is the ID column. Notice that it is numeric here, which is common but not a requirement. We can have multiple tables like the purchases table. It also has an ID. Notice that instead of including the details of the product in the purchases table, we just include the ID of the product that was bought. The same is true for the customer column, but we don't see it here. This is enforced through a foreign key constraint, as we see here. That means there's a relationship between the products and the purchases. It has many implications, such as we won't be able to delete product C because purchase 79 references it. Let's say two users try to purchase products at once. That isn't a problem. The table will add two rows and can handle that relatively quickly. But what if something fails? Let's say I want to add a row. I set all the values correctly, but then due to a bug in the application, I didn't set quantity. Now, the database might be corrupted, and this can cause other cascading bugs when trying to read the data. Databases protect us from that through transactions. When working with a database, we do it with a transaction. A transaction treats the changes as an all or nothing situation. If there's a failure, the transaction is rolled back and the entire set of changes is gone. It's as if we were never there. If we succeed, we commit the changes and they all go in. It's all the changes or none of them. Now, there are many nuances and a lot of fine print related to the level of database reliability, which is a trade-off with performance. But the core ideas are universal for databases. ACID is an acronym that stands for Atomicity, Consistency, Isolation, and Durability. These are four essential properties that a database management system should have to ensure the reliability and integrity of transactions. The ACID principle helps ensure that data in the database remains accurate and consistent, even in the case of errors or failures. Here's a simple explanation of each property. Atomicity states that a transaction, which is a sequence of one or more operations, should be treated as a single unit. A transaction should either be fully completed or not executed at all. If any part of the transaction fails, the entire transaction should be rolled back. This ensures that the database remains in a consistent state and prevents partial updates. Imagine a bank transferring money from one account to another. The transaction involves two operations: subtracting the amount of data from the sender's account and adding it to the receiver's account. Atomicity ensures that both operations occur successfully or neither does. If an error occurs during the process, the transaction is rolled back to the initial state. Consistency ensures that the database remains in a consistent state before and after the transaction. This means that a transaction must transform the database from one valid state to another, preserving data integrity and business rules. If a transaction violates these rules, it should be aborted. If the bank transfers, in the bank transfer scenario, consistency ensures that the sum of balances in both accounts remains the same before and after the transaction, preserving the overall balance in the system. Isolation ensures that transactions are isolated from each other, meaning that intermediate state of a transaction should not be visible to other transactions. Each transaction should appear as if it's being executed sequentially, even though they might be running concurrently. If two customers are simultaneously transferring money between their accounts, isolation ensures that their transactions don't interfere with each other, and each transaction sees a consistent view of the data. Durability guarantees that once a transaction has been committed, its effects are permanent, stored in the database, even in the case of system crash or power failure. This is usually achieved by storing transactional logs and periodically synchronizing data to a non-volatile storage medium. After the bank transfer transaction is completed and committed, durability ensures that the updated account balances are permanently saved and won't be lost due to a system failure. We work with relational databases using SQL, which lets us query and update the database. It's very different from the other languages we discussed so far, as its only purpose is working with data. Let's say we want to fetch the content of this table in SQL. We could use a query like this. The select keyword indicates the type of the query. Data retrieval, this is followed by the names of the columns. The from keyword indicates that the following entry is the name of the table. Typically, commands in databases include CRUD operations. Select falls into the read category. We can add rows, create new tables, update content, and delete. There's a lot to discuss here, but that's a huge subject. When we set up the Spring Boot project, we added several dependencies. One of them is the H2 database, which is really a really simple SQL database that requires almost no setup at all to work. In the real world, we would probably use a more robust DB such as Postgres, MySQL, Oracle, or something like that. But setting up all of those requires a lot of work, so we will work with H2, which is enough for this case. Let's go into the code. We start by creating a new DB package in the Wordle demo project. In this first version, we won't be doing much, but we want to organize the data layer in one place so it will be easy to change. We then create the first class, which is the database class. It will serve as our repository. So far, we worked with REST request, a component, and a service in Spring Boot. Repository represents a database access abstraction in Spring Boot. We can inject this bean just like other Spring Boot beans. We add the required args constructor so we can inject objects into this bean too. The transactional annotation means that the methods in the bean act like a transaction. If someone invokes a method in the bean without a transaction, that transaction begins implicitly as the method enters and is committed when it finishes. If the caller is already in a transaction, then this method will become a part of that transaction. Here is, it doesn't matter much, but imagine a big application with many bean repositories for database access. It might not be simple to know when to commit and when to roll back the transaction. Spring takes care of that for us almost seamlessly. We inject the JDBC template class. JDBC stands for Java Database Connectivity. This is a string abstraction around that API that we will use to access the database. Here I have a few constants representing the queries we will use later on. I could write them in the code, but when you have a value that doesn't change, it's a good practice to define it in a constant like this. That makes it easier to read and modify the code later on. The three quotes syntax in Java is called a text block. It was introduced in Java 15 and lets us write strings that break lines, include quotes, and much more. It's very convenient for longer strings like this. This is a create statement. With it, we create database tables as we saw before and define the columns that will be part of that table. The statement will only execute if the table doesn't exist. That means that we can run this SQL statement and it won't fail if we already created the table beforehand. The table will be named activity. Next, in brackets, we have the definition for the columns. The ID column is an identity. In H2, that means that it's a number that keeps incrementing. This is common for databases, but the syntax sometimes varies. The primary key is very useful if we want to find a specific entry in the database to edit or modify. By using an identity, we let the database handle the complexity of assigning an ID. This isn't a trivial task since many users might add rows to the table and each one must be unique. We don't have a user ID yet, but we will when the application is finished. The varchar is the database's equivalent of a string. Notice we limit the length to 255, which is pretty common. I did that for all the strings here, including the current guess made by the user and the word he was guessing against. We want to know when a guess was made, and we can use a timestamp for that. We also want to know the number of attempts. With all of this information, we can perform complex queries that would do things like calculate the average number of attempts made on Monday. Now that we have the data structure, let's define the other queries. First, we have the insert query, which again has a bit of an odd syntax. We can insert a row into a table without providing all the column values. That's why the command accepts the column names as the first set and then a set of question marks representing the values. The question marks are a special case. When we send the query to the database, it will accept 5 value parameters, one for each question mark. It will then provide those values with the query and let us insert arbitrary values without rewriting the SQL every time. This is more efficient and more secure. The final query is the select query, which we mentioned before. It retrieves all the data from the table. The post-construct annotation in Spring Boot invokes the method after the bean is ready. Here we can write initialization code if necessary. In this case, we verify that the table already exists by running the create table SQL command using the execute method. For the next bit of code, we need to create a new record that will represent the entries within the database. We don't necessarily need it, but it's more convenient to work with a class or a record. The values here should be pretty familiar as they match the content of the table columns exactly. This isn't very creative, but we can easily map it to some of the database APIs as we will see soon enough. Let's go back to the database class. The insert call accepts the code for the insert query and the parameters from the DB entry record. We can invoke this method and the DB entry will be inserted into the database. How do we fetch the data? The select SQL works a bit differently. We need a row mapper, which I will define shortly. To implement that, the mapper takes the raw JDBC results and converts it to a more friendly format. In this case, a list of DB entry instances. We can create a class within a class. This is called an inner class, and it has some special capabilities and limitations. Since this is something internal, I just did that. The implements clause is an important part of Java, which I will discuss more in the next video. An interface is a special type of class. It has no modifiable fields, no state. We can implement many interfaces, which allows us to represent ourselves as that class. This is the basis of an important concept of object-oriented programming, polymorphism. I will cover that more in depth in the next video. When we implement the interface, we often need to implement methods defined in that interface. In this case, the map row method. Spring can invoke that method to translate a row in the result set to an arbitrary object we defined. My implementation creates a new DB entry and invokes the appropriate get methods on the result set to fill it in. With that, the database class is done. We need to open the application properties file in the resources directory so we can define the location of the database and how to access it. This is mostly boilerplate code that is very specific to a database. The first line is the database URL. In this case, we store the H2 file in the current directory for the application. We define a driver, a username, a password for the database, etc. Once this is done, we could tie the database to the code, but it's a bit of a problem. We can just run a simple application and see if it works. But as we have many moving parts, this gets harder. In this case, the database is still simple, but if we have a problem, it might be due to the database, or the services layer, or the front end. I'd also want to automate such problems. If I fix a bug, I want to make sure it doesn't happen again. That's why it's important to run tests to make sure that everything works as expected. The most basic form of tests are unit tests. We isolate a specific part of the application, such as the database layer, and test it. That makes it easier to solve bugs there without going through all the UI layers. Up until now, we did all our work in the SRC directory. We created a new testDB class in the test directory, which is designed for test code. Spring Boot has some built-in support for custom test execution that makes life much simpler for us. By using this annotation, we can leverage a lot of the capabilities of Spring in our tests. Up until now, we only injected beans into Spring with constructor-based injection using the required args constructor and the final field. There's another way to inject beans in Spring with the auto-wired annotation. It's discouraged, but in tests, it's pretty common. Spring will set that object for us seamlessly. Writing a test is as easy as creating a method and annotating it with the test annotation. We can then write code that uses the API we just developed. In this case, I just create a simple record to use for the data and then insert it into the database. We then invoke the select_all method to fetch the entries from the database. If there's a bug in the select or the insert method, the test will fail. But what if there's a bug that doesn't cause a crash? That's where the assert statement comes in. We verify that the list has one element in it, and then have a second assertion that verifies that the entry returned from the select query is identical to the entry we saved. But this test will fail at least after the first run. Since we save entries in the database, in the second run, we will have two elements. We need to prevent the database from saving. Luckily, we have a resources directory under tests2, and it can override the resources we have under src. In it, we can place a different application properties that references a memory-based database. This database will be gone once the tests finish running. If we right-click the tests Java directory and select Run All Tests, they all execute, and IntelliJ presents us with a nice test execution UI and indicates that indeed our database API is working correctly. This helps a lot as we build more elaborate code. In the next video, we will wire this into the code, and following that, we will dig deeper into better ways of working with databases, and we'll discuss more about object-oriented programming. If you have any questions, please use the comment sections. Thank you.